Now in this lecture, we are going to go over finding type 2 error probabilities, which are denoted by the Greek letter beta. All right. So type 2 probabilities is the topic of this lecture. Probabilities, and it's denoted by the letter beta, and along with type 2 error probabilities we also have another associated measure. It's called the power of a hypothesis test, and that is really 1 minus whatever the type 2 error probability or beta is. So we are going to go through the steps. First, we are going to understand what type 2 error probabilities are and what power of a hypothesis test means, and then we are going to go through the step-by-step process of calculating the beta, and then from there how to calculate the power. The formula for the power is pretty simple. It's the calculation of the beta, which is a little more complex. All right, so that's going to be the topic of discussion in this set of slides. In this section of chapter 9, we are going to talk about type 2 errors and their probabilities, and also something called the power of a hypothesis test. Now, before we go deep into this, let's just talk about a few things we discussed previously, or we learned previously, about the two types of errors that are possible when performing a hypothesis test. Now, we said before that there are two types of errors. One is called the type 1 error, and the type 1 error is rejecting a true null hypothesis. Rejecting a true null hypothesis. True null hypothesis. And we said we want to keep the probability of making that kind of error, that is the probability of rejecting a true null hypothesis, very low. And that probability we denote by what's called alpha, and alpha is determined from the significance level at which we are testing. So alpha denotes the probability of making a type 1 error. The other kind of error is type 2 error. A type 2 error is one where we do not reject a false null hypothesis. Not rejecting, we do not reject, so let's write that, we do not reject a false null hypothesis. And the probability of making a type 2 error is denoted by the symbol beta, the Greek letter beta. All right, so alpha again is the probability of making a type 1 error, and beta is the probability of making a type 2 error. Now, in this section, we are going to learn how to find beta. That means how to find the probability of not rejecting a false null hypothesis. What would be the probability of not rejecting a false null hypothesis? And power means the probability of taking the correct decision. All right, so power represents the probability of taking a correct decision, of taking the correct decision. Okay, so given that, we will now proceed and talk a little more about type 2 error probabilities. Now this slide summarizes what we just discussed previously on type 2 error probabilities. Type 2 error probability is the probability of not rejecting a false null hypothesis, and it is denoted by the symbol beta. So alpha is our type 1 error probability, and beta is related to type 2 error probabilities. And if beta is type 2 error, what is 1 minus beta? Now, 1 minus beta, some would think intuitively that 1 minus beta would be alpha. That is not correct. All right, keep in mind 1 minus beta is something else. It's called the power. Okay, so in the next slide, we will talk about that. Now, the power of a hypothesis test is the probability of making the correct decision of rejecting a false null hypothesis. Now, that word is missing here, so I'm going to write that. It is the correct decision of rejecting a false. Let me just use a different color so that it's visible here. Rejecting a false null hypothesis. So that is the correct decision, correct? So that's what the power of a hypothesis means. That is the probability of not making a type 2 error. And the power is calculated by subtracting beta from 1. So 1 minus beta is the power of a hypothesis test. All right. So next we will go on to first finding beta, that is the probability of making a type 2 error. And then once we have beta, finding the power is easy. All you do is subtract beta from 1. Now, before we go into the next few slides, I'd like to take a few minutes to talk about the concept behind beta and type 2 errors, as well as clarify some misconceptions that may arise around the beta. So if we recall, beta is the probability of making a type 2 error. And what is a type 2 error? It is when we do not reject, we make a type 2 error when we do not reject a false null hypothesis. A false null hypothesis. Alpha, on the other hand, is the probability of making a type 1 error. A type 1 error. And what is the type 1 error again? When we reject a true null hypothesis. A true null hypothesis. Therefore, in order for a type 2 error to occur, the null hypothesis must be false. On the other hand, for a type 1 error to occur, the null hypothesis must be assumed true, right? And when we perform a hypothesis test, we always assume that the null hypothesis is true. And we work with alpha, right? We keep the value of alpha, which is the probability to reject a true null hypothesis, low, and the area, that probability, which represents the area under the curve, is the area of the reject region in our curves. If you recall, when we were doing our hypothesis tests, we were drawing a normal curve, and we placed our null hypothesis mean. The null hypothesis mean was at the center of the curve, and based on that position of the null hypothesis mean, the null hypothesis mean being at the center, we created our reject and do not reject regions. If it were a left tail test, then reject region would be to the left. If it were on a right tailed, it would be on the right. And if it was a two tail test, reject regions would be at both ends. But let's assume this is a left tail test. So our reject region will be to the left, and the do not reject region is on the other side of the reject, and the area associated with the reject region under the curve is whatever value alpha is. Typically it's 0.05, and associated with alpha was also what we have a z of alpha value. If it's on the left hand side, it'll be negative z of whatever alpha is in a left tail test. And that represents a critical value. That means the cutoff between the reject, and the do not reject region is the critical value. All right, and then the way we perform our hypothesis test using the critical value approach is we bring our test statistic, which is our evidence, and see whether it falls in the reject region or do not reject region, and based on that we take a decision, correct? So alpha is used when performing a hypothesis test, all right? And in a hypothesis test, when we draw the figure, we assume that the null hypothesis is true. The null hypothesis mean is true, and we always draw a diagram placing the null hypothesis mean at the center. All right, so everything is scaled. All right, the position of the reject region, do not reject region is based on where the or rather what the true null hypothesis mean is, right? Now, the common misconception, all right, intuitively we might think that, well, since beta is the area of the do not reject region, all right, beta, it says, is the probability of a type 2 error, therefore it's the area of the do not reject region, right? And intuitively we may think that if we find the area of the do not reject region in this figure that we use to perform the hypothesis test, we will have found beta, all right? And we may end up doing, to find DNR, the do not reject region in this figure, we just do 1 minus alpha, and we may think that that's our beta value. However, this is incorrect, all right? You cannot find beta from the same figure with which we perform our hypothesis test. This is a complete no-no. This is incorrect, all right? Why so? Because let's look at the definition of beta. It says the type 2 error is not rejecting a false null hypothesis. So what the type 2 error is claiming is that the null hypothesis mean that we use to perform our hypothesis test is in fact false. And when the null hypothesis mean is false, it cannot be positioned at the center of the figure. Now, when somebody is claiming that the null hypothesis mean is false, then they also better give us what is supposed to be the true null hypothesis mean. All right, that if the null hypothesis mean is true, then we must ask them, then what do you think is the true mean? All right, give us an alternate mean. So we should be provided with an alternate mean. Okay, and what happens is we will then use this alternate mean to be the true mean, and we will have to redraw this figure. So what is going to happen is we are going to again redraw our curve, but this time we are going to place the alternate mean, which somebody may claim is the right mean, all right, because the null hypothesis mean that we used to perform the hypothesis test was false. So they better give us a true, what they consider is a true mean, and with that value we will redraw this figure with the alternate mean now at the center. And what's going to happen is the whole diagram is going to get rescaled. We will have our reject region may move further to the right or closer to whatever the alternate mean is, and we may have our reject region now. It'll still be to the left if it's a left tail test. The other region will be the do not reject, but the area under the reject region will change. All right, it will change, it may expand, it may become a broader reject region, or it may become a smaller reject region based on whatever our alternate mean is, the value of the alternate mean is. And the beta value is going to be the do not reject region area, but of the newly drawn figure. You see that? All right. So that is the important thing that we must remember, that beta is indeed the area of the do not reject region, but not of the original hypothesis test figure, hypothesis test diagram, but of a redrawn, regenerated figure where we place the alternate mean at the center. And in the next few slides, we will learn what steps to follow one by one in order to redraw this figure. All right, where the new reject region will be, what the new critical value will be, all right, based on this alternate mean. And therefore, from there, we will learn how to calculate our beta. All right. So this is the example problem that we are going to use to compute the type 2 error probabilities. Let's try to read through this and try to understand what the problem is about and what data has been provided to us. It says here it's questioning the gas mileage claims. The manufacturer of a new model car, the Orion, claims that a typical car gets 26 miles per gallon MPG. A consumer advocacy group claims and thinks that the mean gas mileage of the cars is less than 26 mpg. The group plans to perform a hypothesis test. So they've stated the null and alternate hypothesis. The null hypothesis is what the car manufacturer claims, which is the mileage per gallon is 26 miles. So null hypothesis H sub 0 colon mu sub 1 equals 26 mpg. Again, the null hypothesis must always have an equal sign in it. That's the manufacturer's claim. And the alternate hypothesis claimed by a consumer advocacy group says it is less than 26 mpg. It's less than. So that's why you have a less than sign in the alternate hypothesis statement. That's the consumer group claim. So the question was, at the 5% significance level, using a sample of 30 Orions, find the probability of making a type 2 error if the true mean gas mileage is 25.8 miles. Now, they are saying that they're not asking us to perform a hypothesis test, but they are asking us to find the probability of making a type 2 error given all these information. All right, so the original null hypothesis mean was 26 mpg. Since the alternate hypothesis has a less than, it tells us that it's a left tail test. The reject region will be to the left, and at the 5% significance level, so alpha will be, all right, so alpha, based on this information, alpha would be 0.05, which is also the area of the reject region, And then at the bottom it says, assume that the gas mileages of Orions are normally distributed and the standard deviation is 1.4 mpg. That means this value 1.4 represents the population standard deviation, or sigma. All right, so in the next few slides, we are going to go through the steps of finding the type 2 error probabilities. Okay, but it'll be based on the some of the information that were used or that would have been used to perform a hypothesis test. All right. Now, there are some basic questions we must first answer before we start working on finding the beta value. The first thing is, based on the information we got from the previous slide, from the word problem, we have to know what kind of test is it. Now, the consumer group was claiming that the mileage is less than 26 mpg. So that makes it an alternate hypothesis. If you remember, you can go back and check. The alternate hypothesis said mu sub 1 is less than 26 mpg, right? So that makes it a left tail test. So the original hypothesis test is a left tail test. The significance level alpha would be 0.05 because the question said at 5% significance level, therefore alpha is 0.05. Now, if we were to do a hypothesis test, we had to find the test statistic. That test statistic would be found using this formula. Remember, the population standard deviation was given to us, so we would use the sigma value in our computation of the test statistic, and we would come up with a z value, right? We would use the z distribution. It would be a z test procedure. But we do not need to find this because they're not asking us to perform the hypothesis test, right? Now, we also have to figure out what the critical value was. All right, so if we were to perform a hypothesis test, this is how a diagram would have looked like. All right, so the null hypothesis was claiming that it is equal to, the mileage is equal to 26, so 26 would be placed at the center. So that would correspond to a z value of 0. Because it's a left tail test, the reject region would be to the left. The reject region would be to the left, and this area under the curve, which corresponds to the reject region, would be an area of alpha equals 0.05, and the cutoff, the CV, the critical value, all right, this is the cutoff. That means the cutoff which separates the reject from the do not reject. This side would be do not reject, correct? Do not reject, and this cutoff point, this critical value would be, because it's on the left hand side, it would be a negative z of 0.05. And if you look up your table or find it from your calculators, you will get a value of negative 1.645. And we have to note that value because we are going to use it when we will be finding our when we will be computing the beta value. All right, so we have to note the critical value. If it's a left tail test, it's going to be a negative 1.645. However, we can just write it as z of alpha by 2. All right, we don't need to show the sign, although the critical value would be negative because it's on the left hand side. But for our purposes later on, we will not need to use the negative value, and I'll tell you why. All right, but let's just go on to the next few slides to complete the process. Now, before moving to the next slide, something caught my eye in the previous slide, and it was that this critical value here, as you see, is alpha by 2. In a left tail test, we do not have alpha by 2, so it would be just alpha. All right, so you may want to correct that in your previous slide. I'm not able to go back and change it because I've already recorded over it, and I don't want to erase the entire recording just because of that. But just know that for a left tail test and a right tail test, this would be just z of alpha and not z of alpha by 2. For a two tail test, you would have to find z of alpha by 2, correct? Now here is a diagrammatic representation of the null hypothesis, or rather of the hypothesis test, all right, that we talked about on the Orion cars. So they have here in this figure and under the normal curve, they have the null hypothesis mean, which was 26. The null hypothesis mean was claiming the MPG to be 26, so they've placed it at the center of this curve. And over here on this side, you see the reject region like we drew previously. The reject region is to the left and the do not reject region is to the right hand side. And then the reject region, the alpha value, the area under the curve corresponding to the reject region is alpha equals 0.05. What they have here, however, is not the minus 1.645, right? Previously, we said that this area, or rather the cutoff, the CV, remember, we found was negative 1.645. But what they found here with this 25.6 is the X bar value which corresponds to the CV. All right, so 25.6, our CV, our critical value that we came up with was Z of 0.05, which we said was negative 1.645. But what they have found is the X bar value. The X bar value corresponding to a Z value, to a Z of negative 1.645. All right, and that's an exercise we will have to perform as one of the steps to get to the beta value, to get to calculating the beta value. All right, so we can, if we know the formula, that we use to find our test statistic, which is Z of X bar minus mu sub 0 divided by sigma over square root over n. All right, this time normally we have our X bar values, the null hypothesis mean, the sigma n values, we plug them into the formula and we find our Z. This time we know our Z, which is 1.645, right? We just have to plug in the values we know and solve for X bar. All right, and that will give us the value of 25.6, and that's how they got the value of 25.6 for this particular problem. So here they are actually going through the process of coming up with the X bar value. So for the type 2 error probability, we first determine the X bar for the critical value, which was negative 1.645. Negative 1 for this particular problem. All right, if it's a different problem and a different alpha, different significance level, we will end up with a different Z value depending on which side our alpha reject region would be. Now in this case, it is the sample mean that is 1.645 standard deviations below the null hypothesis population mean of 26, right? What it means by below the null hypothesis population mean is just this, all right? So we have our curve, all right, and our center point is here at 26, and it's 1.645 units below the null hypothesis mean. So because it was a negative 1.645, this Z value, we have to find a corresponding X bar value. All right, X bar value, which is 1.645 standard deviation units below because it's on the left hand side. That's why we use the word below. All right, now the formula to use is mu sub 0 minus Z of alpha times sigma divided by square root over n. Correct? So minus because it's a left tail test. Whenever it's a left tail test, remember our z value was negative 1.645, so that's why it's negative z of alpha. And plug in the value. All right, so if mu sub x bar equals 25.8, then we'll just find, all right, that way how we get our x bar value of. Now in the previous slides, we had found our critical value and the corresponding x bar value that went with the critical value. So in other words, we had the diagram here when our null hypothesis mean assumed to be true was at the center, and that value was 26 miles per gallon, if you remember. And then we had our reject region to the left, and which had a significance level of 5%. That means this alpha value had 0.05 for its area, for its value. And we also found that the corresponding z of alpha was or rather negative z of alpha, because it was on the left hand side, the negative z of alpha was negative 1.645. And in the previous slide, if you remember, we found the corresponding x bar value. This was the z of alpha value. We found using a formula the corresponding x bar value, and that was 25.6. So when 26 was at the center, the x bar value corresponding to the critical value was 25.6. All right. Now we have to find the type 2 error, or the value of beta. Now keep in mind that beta means the null hypothesis mean is not true, right? That's what beta, by definition, it's type 2 error, right? Type 2 error, and type 2 error says do not rejecting a false null hypothesis. A false null hypothesis. So that means we are claiming that this 26 that the manufacturer claimed, 26 mpg, is not the correct mean, all right? It's a different value. So whenever somebody claims that the null hypothesis mean is false, then they better give us what then is the correct mean. All right, so here they have given us a mean value of 25.8 mpg. So that's our alternate mean. All right, so I may as well write here mu sub a. That's 25.8 mpg. So to find our type 2 error value, we must redraw this diagram, this curve, keeping 25.8 at the center of the curve. So previously we were using 26 as the null hypothesis mean, and we placed it at the center. But now that this is not true, then we replace this 26 by 25.8, and when we do that, this whole picture changes. All right, so what happens is 25.6 is still there. All right, the critical value 25.6 is still there, the x bar value corresponding to the critical value, that is. However, you see the reject region has expanded. All right, the reject region is still to the left, but it's a much broader reject region. So the graph has been rescaled now based on the new mean given to us, 25.8. All right, so 25.8 is here, 25.6 is now much closer to the center than it was previously. Okay, so what we do at this point is we have placed 25.8 at the center, which will be 0 for our z value. We have to find the Z value corresponding to 25.6 X bar. So it'll have a new Z value. Okay, it'll not be negative 1.645 any longer, because you see that it's shifted more towards the center. The critical, the cutoff has shifted towards the center. It will be a different critical value based on the new mean. All right, so the formula to find that is the same as finding any Z value, right? So X bar equals 25.6. So they've used that same formula, X bar. All right, so let me just put the corresponding values of the variable. So 25.6 is the X bar, and then minus 25.8 is the new null hypothesis mean, which is, in other words, the alternate mean that was provided to us, divided by sigma. So 0.26 doesn't change from the previous. It's sigma divided by square root over n. That's how we got 0.26. And we came up with a value of negative 0.77. And that's the new Z value for 25.6. Okay, and why did that happen? Why did the Z value change? Because we used a different mean at the center, all right, from what we had used previously. Okay, so now that we have found the new Z value, this we have rescaled the diagram and found the new Z value. Okay, it's just a second, it's a new Z value. We have to find beta. Beta will be this area of the new diagram. All right, so this shaded area is what beta is. So it is area to the right. Okay, in a left tail test, because the reject region is to the left, the do not reject region will be to its right. So we can find the, using the table or using your calculators, you should be able to find your beta value. So, but here the beta is area to the right. So first, if you're using the table, first find the area to the left and then perform 1 minus whatever area is to the left will give you the area to the right. I'm trying to get my pointer up here. So this is the area, right? So your table, keep in mind, only gives area to the left. So to find the area to the right, you first need to find the area to the left from your table, and that area is, it says area to the left of Z is 0.2206, right? So let me write that here. It's, this area is 0.2206. So the area to its right will be 1 minus 0.2206, which is equal to what they have here, 0.7794. All right, so, and that is what the area or the value of beta is. Now, if they ask you to find the power, all you do is 1 minus beta, which is 1 minus 0.7795. Now here we are summarizing the steps we follow in order to find the type 2 error probabilities. Purpose to find type 2 error probabilities for a one mean Z test when the true population mean equals an alternate mean. Here are some assumptions. It has to be a simple random sample. Number two, it has to be a normal population or a large sample, because if it's a large sample, then it automatically becomes a normal population. It is assumed to be a normal population if the sample size is large. And then the number three is very important. The sigma must be known, because if the population standard deviation is known, then we can use the Z procedures for our test. All right. Now, step one is to find the X bar critical values. That means we we use our alpha values to find our z value first, the corresponding z value, and then once we know our z value, we have to find a corresponding sample mean that goes with that critical value. And there's a formula for that. If it's a two-tailed test, it's mu sub 0 plus minus z of alpha by 2 times sigma divided by square root over n. So if it's a two-tailed test, it's z of alpha by 2. All right, and there's a plus minus because a two-tailed test is double-sided, therefore it'll be there'll be a reject region to the left, there'll be a reject region to the right, so that's why there's a plus minus in it. If it is a left tail test, then it has the formula has a minus and it's just z of alpha, not alpha by 2. And if it's a right tail test, the formula has a plus and it's again z of alpha because it's a one-sided test. All right, the formula will be provided to you in the formula sheet. You just have to look it up, and based on what type tail it is, you will just need to apply the correct formula. So these are the formulas to use, where mu sub 0 is the null hypothesis value of the mean, alpha is the significance level, sigma is the population standard deviation, and n is the sample size. In step 2, we go on to finding the probability of a type 2 error beta, which equals the area under the normal curve with parameters mu sub a and sigma divided by square root over n that lies between the two x bar critical values for a two-tailed test. So in other words, let me just quickly draw a picture for the two-tailed test. Your do not reject region. Remember, for a two-tailed hypothesis test, there are reject regions on both sides. All right, both sides reject, and then do not reject is at the center. All right, so this is going to be our beta value. And then for one-sided, if it's a left tail test, then the do not reject region will be to the right because the reject region will always be to the left. And if it is a right tail test, then the do not reject region will be to the left. However, in order to find these areas, we have to rescale our diagram. We have to rescale our diagram by replacing the center with the alternate mean mu sub a. All right, so we have to find the z value corresponding to the new alternate mean, and we went through that exercise. I explained that in the previous slide. All right, you may want to just go and revisit it if you're not too sure about it. Okay. Now here is a picture which is rescaled based on different alternate mean values. So 25.8 is a possible alternate mean. Then there's a 25.6, 25.3, and 25 with alpha, the significance level, at 0.05, and n, the sample size, equals 30. And let's just go through these four diagrams. You see over here in the first diagram, all right, 26 was shifted to the right of where it was originally. Remember, for the hypothesis test, 26 was at the center. When we replaced the 26 with 25.8, 25.8 took the center point and 26 would move to the right. Okay, 26 is greater than 25.8, so it would shift a little bit to the right. So this was a rescale diagram, and we use 25.8 as our alternate mean. All right, and based on that, our do not reject region and the reject region were defined. All right, and then if the alternate mean were to be 25.6. 26 would shift further to the right, with 25.6 being at the center, and our do not reject region, as you see over here, has become smaller. This region has become smaller than in the previous picture. All right. When we replace 25.6 with 25.3, 26 has moved further to the right, and our do not reject region has become even narrower. And finally, when we replace replace the null hypothesis mean with 25, you see, we have a very small area for beta. So this is just showing us how the areas of beta, all right, how the area changes based on the different values of the alternate mean. And as you can see, the reject region still stays to the left, all right. It's a left tail test. Reject region still stays to the left, but as we keep changing our alternate mean values, the reject region is becoming broader and broader, all right, and beta is becoming smaller and smaller. So the power of a hypothesis test is the probability of not making a type 2 error, that is the probability of rejecting a false null hypothesis. The formula for it is power equals 1 minus the type 2 error, the probability of a type 2 error, and the probability of type 2 error is denoted by the symbol beta. So in other words, it's 1 minus beta. In other words, it's whatever the area of the reject region is in the newly defined diagram, in the newly scaled diagram that we get after replacing the null hypothesis mean with an alternate mean. Now we can create what's called a power curve table, all right, a power curve table using different alternate means. So in the previous slide, we came up with diagrams with different values for the alternate means. And what we can do is we can use different alternate mean values, find the corresponding type 2 error probabilities, the beta values, using the same steps that we learned before, and come up with the power by subtracting beta from 1. And once we get all these power values, we can plot what is called the power curve, as we will see in the next slide. Now they've given here the steps to come up to complete the table that I just showed previously in the previous slide. And once we have that table before us, we have to plot the values in the first and third columns of the work table from step 2 in the previous slide as points on a graph with mu on the horizontal axis and power on the vertical axis. So it will be like a graph where the horizontal axis will contain different values of the alternate means, okay, all mean sub A1, mean sub A2, and so all that, right? And the vertical line will have the power values, the probability values of the power, and then we will connect the points in the graph from step 5 with a smooth curve, and this is what it's going to look like. All right, so over here, as you can see in the diagram, on the x-axis we have all the different alternate mean values, right? 24.8 from lowest to highest, 24.8, 25, 25.2, 0.4, 0.6, 0.8, all the way to 26, and these are for different sample sizes, right? N equals 30 and N equals 100. And here we have the different power probabilities. All right, the probability of taking the correct decision. That's what power of a test is. Okay, so they've plotted the different 1 minus beta values, and then you just connect them with a smooth curve. And finally, here's a relationship between the sample size and power for a fixed significance level. Increasing the sample size increases the power of the test, right? So if we are using a 5% significance level, which is the most common significance level used to perform a hypothesis test, if we want to increase the power, one way is to use a larger sample size, right? So given a fixed significance level, increasing the sample size increases the power.